Good evening, everyone on the call. Gonna ride on the already observed protocol. It's a great privilege to be here, and as has been mentioned from the very beginning, we're going to be talking about 4 topics. One of them is machine learning and artificial intelligence, and we'll look at why we utilize AI and how we can get involved in utilizing that. We're also going to look at cloud computing. We're going to look at data, and then we're going to look at DevOps. Okay, without much ado, let's get started. So I've already been cited. I will go ahead and skip that slide and jump straight to artificial intelligence. In the past, artificial intelligence, while it was called artificial intelligence, we majorly spoke about machine learning. But nowadays, it's generally called AI because it's gone past that machine learning point that we were at. So let's talk about what artificial intelligence is. To keep it simple, because I think that simplification helps to just take the cloud or the shroud off any topic, to make it simple and to make it approachable for people. Artificial intelligence really is just the quest to make computers think and act like humans. That's all it is. It's the same sort of thing as your standard programming, but the difference is that with standard programming, you provide the rules, you specify the rules, and then the data, you provide the data, and then you end up with an outcome. Right, so you think of standard programming like if you had to write something that would convert temperature readings from Celsius to Fahrenheit, you would use rule-based programming. With artificial intelligence, what you do is you take your observations and you take your data, and then you try to arrive at the rules from that, okay? Now, the rules that you try to arrive at, we typically call that the model. So it's called AI, but it's really a model. And you would think of models from the fact that you've heard of large language models, right? So that's that model. But a large language model is a specific type of model. Now, the model itself is a tensor, and a tensor is a multidimensional matrix. And we will come back to talk about the multidimensional matrix in a little bit for you to understand why we have certain types of computational requirements when we talk about machine learning. Right. Now, we've mentioned that the model is a tensor, so everything is a mathematical operation when it comes to artificial intelligence. There are 2 stages to artificial intelligence. And so if you look at the photograph to the right, there's a training phase and there's an inference phase. In the training phase, you try to get the model or arrive at the model. Now, what you do in the training phase is you formulate a hypothesis. And once you see this hypothesis, it's really very simple and straightforward. Your hypothesis is y is mx plus c. And it turns out everyone has done some sort of machine learning at a very simplified level, right? Back in secondary school, we all did maths and we all did something called the line of best fit. And that's what, ML training is. You try to find the equation that describes a line. Of course, back in secondary school, you would tend to try to find a straight line, but we all know that a line is a line. It doesn't have to be straight, right? It could be curved. And so you try to find your hypothesis. Now, you have your data, which we will call X, and you have your observations, which we will call Y. So you try to find 2 things, your M and your C. Your M being your, again, let's just call it the line of best fit to simplify it. And then your C being your point of intersection of the vertical axis. Okay, so if you remember that, machine learning becomes straightforward in terms of what you're trying to accomplish. So you're trying to find M and C. Now, your X, unlike in secondary school, isn't a one-dimensional value. It's not a scalar value. And it's not even a vector, right? So now we go back to our tensors. So it's a multi-dimensional matrix. And the reason why it's a multi-dimensional matrix is that we tend to take data and just stack it, okay? So when you think of something like an image, and just think of something like even just a black and white image, a black and white image is a bunch of what we call RGB values. But if it's black and white, it's really just a range from 0 to 255, which defines the intensity of light at every spot. So if you have a simple image, you will have a height and a width, right? That defines the size of that image. And then you'll have dots. Every dot has a light intensity, and that defines an image. Now you can take all of those values and put them into a matrix, right? And you have a matrix. And so, it starts to make sense that you are now dealing with a mathematical object. Now, if you go from your grayscale image or black and white image to a colored image, you will then have red, green, and blue values in various intensities. So every spot has 3 values, red, green, and blue. So it turns out that you can arrange those values in layers, right? And then you end up with something like a cube. So instead of just a flat image, you end up with a cube. And that cube is a multidimensional matrix or a tensor, okay? So once you have that, then your observations, so you have your X now, you have then your observations, and your observations could be various things. It could be that you're trying to carry out a classification. And if you're trying to carry out a classification, then what you're doing is you're taking your Y and you're cutting it off somewhere, right? You're deciding that if Y is above a certain value, then it falls into one class. And if it's below a certain value, it falls into another class. All of that sounds theoretical. Apologies for that. But a very simple case in point is, if you're looking at images and you're trying to decide as a computer, is this a cat or a dog, right? Then you can have a model. You can train a model where you say to the model, here's this image, and this image is a cat. Here's this image, and this image is a dog. And you do that lots and lots of times. Again, I'm simplifying the training process, but you do that lots and lots of times, and it keeps looking over the images and deciding, trying to figure out, okay, I've got this tensor here, and you say this is a cat. I've got this other tensor, and you say this is a dog. What's the difference? How can I tell the difference between the cat and the dog? And eventually, when it figures all of that out, then it would have had an M, which is your model now. Would have arrived at that M such that every time you multiply M by X, where X is the numerical representation of that image by the model, and then you add C, but again, we can remove C because we can merge it into M. You will then arrive at your Y. And if what you're trying to do is a classification, then you can split, you just have your split, the point at which you decide whether the image you're looking at is a cat or a dog, right? So now this process of refining your hypothesis, of trying to find your M, your model, that's what we call machine learning. And there are various approaches to it. One approach is called a loss minimization approach. Another approach is called a maximum likelihood estimation. So the first approach is more mathematical. Second approach is more statistical. Well, with all of that mouthful of a process, you can then understand that the problem that computers have when it comes to that training phase is how quickly this computation can happen. And really, CPUs have never been good at this sort of operation. And it turns out that there's a very good reason why something called the GPU exists. So the CPU is just your central processing unit. It's useful for certain tasks, computational tasks, but it's not useful or it's not good at linear algebra. Whereas your graphics processing unit is good at linear algebra, and that's why it's great for gaming. It's great for editing movies or even photos and things like that. So where you're going to have machine learning training, you tend to have GPUs in place, graphics processing units. And so if you remember from the last masterclass, Alex was talking about GPUs. So GPUs speed up the training process, and they speed it up so much, it's unbelievable. So without GPUs, it would take you forever to train a very simple model. With GPUs, it makes it much faster. It shortens that period. And so the advances in GPU technology and even CPU technology have made it possible for us to have way more advanced models. Now, there's also your X. Your X tends to be your observations, and you tend to require a lot of observations. And so what that means is you need to store a large amount of data. So for training to happen, you need powerful computers, and powerful computers consume a lot of power just to run, but they also emit a lot of heat, and so they require power again for their cooling. So you require powerful computers, and an example of one of those is what you have on the upper image. So that's like a HP ProLiant server. It's filled up with hard drives because you need to store your training data. You don't see what's behind, but you tend to have redundant power supplies, redundant cooling, and sometimes the data might not even physically be on the same machine. So you might have some very complex fiber optic networking to move data back and forth. You tend to have a lot of memory because you need to hold data in memory instead of going back and forth reading from hard drives. And then you have your GPU clusters that can be equipped in machines like this. Some ridiculous number of GPUs tend to factor in when you're talking about the training phase. Once you're done with the training phase, you then have your model. And then what you have is the inference phase. The inference phase, compared to the training phase, requires very minimal computational resources. But again, depending on the size of the model, you have to make your choices for the kind of hardware that you run inference on. But the good thing is we're able to run inference on really what I call low-end hardware. Case in point is most smartphones now have the capability for you to talk to them and then they respond. And a phone is a computer, right? So you tend to have models on phones that do speech recognition, can do text to speech, so you can run your searches, you can activate various applications on the phone. But again, you can run inference on hardware such as this Raspberry Pi that you see here. This is a Raspberry Pi 5 running something called an AI hat. The hat is a hardware attached on top. And so you're able to then run models that will carry out inference. So you can take this sort of device and run it on the edge. When we say on the edge, what we're saying is it's not in a server room. It could be somewhere out in the forest doing something. And that's something, it varies. You have applications where you might monitor for logging. If you have illegal logging activity, you could monitor for poaching. So you can have cameras, just constantly surveilling, sending images back to this sort of device, and then it can look at the images and figure out what is in the image. You can use microphones to detect different types of sounds. So do you have sounds of like chainsaws? Do you have sounds of like gunshots? Do you have sounds of speedboats? You know, if you have maybe illegal border crossings and things like that, all sorts of things. So at the inference stage, you're not training the model. You're just taking the model. One problem that you have, of course, is just taking that model and keeping it. What is the size of the model? Nowadays, you have models in the gigabyte size. And then you need to run your mathematical operation again through that model. So now what you're doing is you're just, instead of, with the training phase, we used to have like back and forth movements. Here you have just one straightforward movement, which is just that computation. But depending on the size of the model, that computation can take a while, you know. So if you're looking at large language models, you hear things like 2 billion parameters, 7 billion parameters, 27 billion parameters, 9 billion parameters. That's kind of like the number of computations that need to take place, right? So when you see like a 2 billion parameter model, when you pass your data through it, there are nodes that you need to carry out computation through multiple stages. So again, it's a tensor. So it's linear algebra, it's vector arithmetic, but there are a bunch of them. Of course, these operations tend to be what's called vectorized. So it's not exactly the way you think about it. Unless you're very good at linear algebra, it's not exactly the way you think about it that it happens. But the point is, you know, it's not black magic. It's pretty straightforward. So, you know, AI has two phases. One phase requires a lot of power, and that's where we're talking about server rooms and GPU clusters and things like that. The other phase, which is the inference phase, doesn't require a lot of server resources. It just requires deployment. Okay, so back to my bullet point. So the operations require vector multiplication, right? Now, why do we use artificial intelligence, or why do we need artificial intelligence? Really, artificial intelligence speeds up what you can do. That's how to think about it. Let's take a medical application where you're analyzing X-ray images. So typically what would happen is if you were running a hospital or an imaging center, you would have people come in for X-ray imaging. You would print out the images, and then you would need a specialist to go over the image and figure out what's wrong. So the bottleneck usually isn't in imaging. It's in the specialists looking over the images and figuring out what is wrong with the image. And so you always have limited capacity depending on how many specialists you have who can look over your images. And there's always human fatigue. So there's a limit to how many people you have. There's a limit to how many hours they can work in a day. If you try to overwork them, you know, the brain is the brain, right? It starts to shut down. And so they just can't see things clearly. Computers, on the other hand, once you train them to analyze the images, of course, they also have their own capacity, but they will usually work faster without fatigue when compared to the human workers, the human specialists, right? And so that's where AI comes in, where you just ramp up the amount of work that you can do. Same thing with like sounds of logging and poaching, right? If you want to, let's say you have a game reserve and you have to combat logging and poaching, without artificial intelligence, what you have to do is you have to station rangers everywhere. There's clearly a limit to how many rangers you can station, but rangers, again, are human, so they need to work on shifts. They can get tired, they can fall asleep. But where you have devices, you can have, you know, as many devices as you can afford. You set them up, just make sure that they're powered, and that's it. They will listen, they will analyze, and they will send out alerts whenever, you know, that threshold is hit. Same thing with like images with weapons in them. So you can have cameras. So imagine a city. How many cameras can you have in a city? High quality cameras. You can have lots and lots. But how many people do you want to have who are sitting down and analyzing images and saying, oh, I see a weapon here, or I see blood here, you know, I see something that looks like violence in this image? you'll need to have a ton, an army of analysts. But where you have AI that is trained to detect these things, then all you have to do is have the right number of servers, connect your cameras to these servers, and just let them do their stuff. Okay, so that's artificial intelligence. And so before we get into data, I will pause for questions. And feel free to ask questions, even if I didn't talk about something. And yeah, I'll do my best to respond to that.
So I think in the absence of any question, we can move by because I'm sure everybody's glued to what you're going to say next. We're already excited about what you're saying and see the next slide now. Everybody just wants to listen to you. Maybe after the class, we can take questions. Thank you, sir.
That's fine. Right. So remember that we said that in order to train ML models, we need data, right? So it's our data and our observations that help us to train models. And so what that means is that without data, you can't train ML models. And we also mentioned it in the last masterclass. Alex mentioned it, where someone asked a question about not seeing Africa-specific data online. We don't have a lot of Africa-specific data online. And for that reason, we also don't have a lot of Africa-specific models, right? There are models that work well in other parts of the world that just don't work well here because they are not trained on our own very specific data, right? And so we have the saying, data is the new oil, which is, you can look at it from various perspectives, but basically, if you think about it from just the perspective of, oil makes money, data makes money, right? Oil drives vehicles, data drives AI, ML, all sorts of things. So you need data. Now, when we talk about data, we're not talking about data in your Excel spreadsheet. Data in itself, in the past, it used to be called big data. Now it's just called data. It turns out that there are things that were large a very long time ago that are, even unimaginable right now. I remember back when we were in the university, we used to talk about storage media in terms of 5 1/4 floppies and 3.5-inch floppies, and you could store 1.44 megabytes. So back then, a zip drive, which I think was it 100 megabytes or so, was something, to talk about. But nowadays you have flash drives with gigabytes, and I think they've even got
terabytes.
Yes, so what was big data is nowadays just called data. So when we talk about data, we talk about the characteristics of that data. And usually there are four V's when it comes to data. So the first one is the volume, and that is how much data are you dealing with, or how much data are you generating. The more data that you have, the more you're able to analyze, and the more you're able to come up with something useful. Now, when you talk about the volume of data, of how much you're generating data, you don't think about it from the perspective of you manufacturing the data. You think about it from the perspective of how that data is being generated or produced. So let's take a very simple example. If you look at a manufacturer like Boeing that makes airplanes, Boeing has sensors on airplanes for almost everything. There's a sensor for almost everything. You turn on a light, there's a sensor. You use the call button, there's a sensor. You go into the restroom, there's a sensor. But we're talking about, we're thinking about just data that is being generated by humans, right? But the engines are generating data, right? Some of that data ends up in the black box, but the engines are generating data. The mechanical systems are generating data, so like the wheels, the wings, you think about it, it's generating data. In the cockpit, they're generating data, cooling systems, HVAC, humidity, ventilation, generating data. Everything is generating data, right? And that's just on one plane. So when you talk about volume, imagine all of the planes that they have generating data. When you think about cars, it's the same thing. Think of any modern car, is generating data. That's why you have a brain box. You have something called a CAN bus. If you connect to the CAN bus, you can read ridiculous amounts of data. So depending on the volume of data that is being produced, you start to have the problem of how do I even store this data? Okay. Now, volume is just one thing. So volume could be, oh, we're generating, 10 terabytes of data daily. We're generating 100 terabytes of data daily. And then there's velocity, which is how quickly is your data growing. So again, if you generate, 10 terabytes daily, then you might estimate that in a year, you're going to store, 10 times 365. The problem is you're not factoring in the new systems that you're designing and producing. So what we're saying is this. Suppose you're an automobile manufacturer and you know exactly how much data one vehicle produces daily. How many vehicles do you have out in the field is one question, but how many vehicles are you producing and selling on a daily basis? So it's not a linear equation, it's an exponential equation, right? Where you need to worry about the data that you're currently generating plus the data that you'll be generating once those generators are out in the field. So volume and velocity just account for the kind of data that you need to store. But there's also variety. And variety just means, again, let's go back to even the vehicle. There's data that is being generated by the engine on its own. There's data that's being generated by the cooling systems. There's data that is being generated by mechanical systems. So your wheels, what causes you, to move. But there's also data that is being generated by the braking systems. It helps you understand the driving patterns of individuals and why things might break. Data being generated by vibration sensors, data being generated by accelerometers, all sorts of data is getting generated. So what the kind of questions that you can answer is a function of the variety of data that you have. And then finally, there's the value that you can extract from the data. So when you store all of this data, the question becomes, what value can you extract from your data? And these questions are not necessarily always easy to answer. It's a function of the business problems that management comes up with. So usually management would want to say, so we hear that brakes are failing in our 2023 model vehicle X, right? Can you tell us why that is happening? So in the past, you might just say, oh, let's go ask the manufacturer of component A. But now you want to look at all of the data and figure out why it is that you're having those sorts of failures. And okay, so now let's talk about storage. So we've talked about data, we've talked about the 4 V's. The question becomes, how do you store the data? Now, remember that we talked about variety, right? You've got data coming from different places, but again, all your sensors are not the same, right? So there's data that you collect periodically. Let's take a very simple example. Engine temperature is kind of data that you can collect periodically. And this will be a value, right? Because engine temperature is just going to be a scalar value. It could be centigrade, it could be Fahrenheit. If you like, store it in Kelvin, right? But where do you store it? On the other hand, you might have onboard cameras. And so you might be, recording video or even just taking still images periodically. how do you store those? You might have microphones, right? So if you're capturing sound, how do you store that? And that's where we talk about files. Things like images, videos, sound can easily be stored in files. Things like the engine temperature is what we call a time series. It's something that you just read consistently at intervals. That needs to go into a database table. Could it go into an Excel file? Yes. But we're really, not going to look at things like Excel files because, at best, you might be able to do something for a few hours, but after that, they're out the door. So you have to think about storage. What sort of data are you collecting? Where are you storing it? So data could go into files, it could go into databases. There are different types of databases. So we won't dwell too much on those. It depends on the kind of data that you're storing, but you've got relational databases, you've got time series databases for things like these data points that you collect at intervals. You could have object-oriented databases. You have vector databases now, and some other ones that I'm probably not mentioning right now. Now the collection, when you look at all of how you're storing the data, whether in files or in databases, one of the critical considerations that goes into how you store your data is how you're going to retrieve the data afterwards. So it's all well and good to store data, but if you're storing data that you cannot retrieve, then you start to have a problem. And so we've had a progression for storage systems where we've gone from files to databases to what we call data warehouses. Now, with data warehouses, what we've had is when you deal with data, you kind of deal with data in two different dimensions. In one dimension, you deal with data in what's called a transaction processing format. An example of transaction processing format is take an e-commerce website. So with the e-commerce website, people are coming and they're asking simple questions like, what do you have for sale? And then they're choosing what they want and, checking out, right? So think Amazon, for instance. I can go on Amazon and I can search for books, I can search for computer parts, I can search for clothes, right? So that's online transaction processing. How the data needs to be stored and retrieved for transaction processing is completely different from the kind of questions that management would ask. So management would ask questions like, what were the top 10 best-selling products last week? What were the top 10 best-selling products during Black Friday? What are the top 10 best-selling products based on discount value? So discount value is basically saying this was the original price, but we did a sale. How many people responded to the sale? Those sorts of questions. Those questions are pretty difficult to answer with transaction processing databases. And so they're usually offloaded to warehouses. And those are called analytics processing systems. So data warehouses are used for analytics processing where you're answering business questions or any other type of question where you want to get insights. With your transaction processing, you don't really get too many insights. And if you try to get insights the way that you want them, you would end up bottlenecking and crashing the system. So we have data warehouses. And then we have data lakes. Data lakes are just a collection of things that are not only warehouses. That is data in different formats. So you could have your warehouses, but you could also have your images, your videos, and things like that. So that's storage in short. Databases or data storage is where you need to think of when you want to start storing your data. And so when you get your data in, you need to get your data out. And that's where data engineering comes in. So when you have your standard system, a lot of the time your data will go into databases. Now, the data needs to be pipelined from your databases to your data warehouses or your data lakes. And it's not just going to end up there getting siloed. It's also going to have to move. So data engineering is just the business of moving things around, not necessarily of refining them. There could be a little bit of refining, but just think about pipelines. So think about your entire infrastructure as the refinery, but think of your engineering as the pipelines that move the data from one spot to the other, right? So data is the new oil. You can't move oil without pipelines. You can't move data without pipelines. Okay. Now, again, remember, we're talking about massive amounts of data, right? We're not calling it big data, but it's still massive. So the problems are numerous. The problems are not as simple as help me put this file on a flash drive. Sometimes the problems are kind of like, this thing happened 2 hours ago. I need to be able to analyze the data. Why isn't the data available for analysis? That's the kind of problem that we're talking about. And so you have the field of data engineering where they just deal with these sorts of problems. So once the data has been moved from where it's being generated to where it's being stored for analytics purposes, you then have analytics and visualization, another field in that whole ecosystem. And what the basic difference between analytics and visualization is that visualization gives you charts and graphs, images are worth 1,000 words. So with visualization, you're able to get the data in a format that is digestible. Now, that format in itself could be either static or dynamic. Static is what would go into things like annual reports or just reports that need to be printed out, PDF format, paper format, whatever it is. Dynamic is where you have people go on a dashboard and change certain values to ask questions, right? So I might want to know top 10 selling items from last week, but I might also want to know top 10 selling values from yesterday. So I need to change the values. That's what makes it dynamic. But then there could be, ever more complicated questions that we need to answer. Visualizations are helpful. They help you see patterns in your data. So things like, do I have seasonality in my sales data, right? On a weekly basis, what days of the week do I have the most traffic? What days of the week do I have the least traffic? On an annual basis, in what months do I observe the greatest traffic and the least traffic, and usually you plot this on a daily basis, but seasonality shows up when you have enough data, 3 years, 4 years, 5 years, then you start to look at seasonality, but you need that in a visualization. Analytics, on the other hand, will ask questions, and usually these are statistical questions. We'll ask questions, come up with the answers. The problem with answers that are not visual is that different types of data could give you the same statistical values, but have different properties. And talking about it now, maybe I should have illustrated one. So we have something called an Armstrong quartet that shows you 4 different data sets that when visualized look different, but they have the same statistical measures, mean, median, mode, standard deviation, all of those things are the same. So, there are times when simple statistical answers are sufficient for you to make a business decision. And there are times when you need to see what you're talking about in order for you to make sense of what's going on. Right. So that's analytics and visualization. And then we have data science. And data science or data scientists, what they do is they try to figure out the best ways of dealing with certain types of data. So remember we talked about variety, and then in analytics, we talked about things like patterns. It turns out that various data have various characteristics, and if you treat them the same, you might not arrive at the answers that you're looking for. So data scientists work in a research capability to try and determine how exactly you should deal with certain types of data. So for example, if you're dealing with banking data and you're trying to figure out whether there's fraud in that banking data, you shouldn't treat that data like medical data, even if the values are the same, right? So one of the things we didn't talk about in machine learning training is that there are different things that come together, different mathematical approaches or statistical approaches that come together to help you arrive at your model. So those different things, that's where data scientists come in, because they tend to work on researching those various approaches to arriving at a model, to optimizing a model, to reducing loss, and all of those sorts of things. So data scientists usually are hired by large companies who do research, and it is the kind of work that data scientists have been doing that gives you things like large language models or generative models, whether you're generating text or generating images or even generating speech. That work comes from data scientist work. It's not the same kind of work as what your analysts are doing. So, with analysts, what you're asking is, why is this thing breaking down, right? Can you look at the data generated by all of the machines and tell us why this thing is breaking down? Data scientists, on the other hand, would give you models, coming again from data, but then those models let you do other types of things. And so those models can be used by analysts. They can also be used by engineers, machine learning engineers, or AI engineers, not data engineers, but AI engineers. Okay, I'll pause again, just in case we have any questions before I go to talk about the cloud. Okay. All right, nothing yet, but yeah, feel free. If we're gonna have any questions, it's fine. If not, we can move on.
All right, Mr. Roberts, maybe I should ask
Yes.
a question and help my people out. Okay, you mentioned something now, and I like it so much, about the different roles. I think we've identified about 3 roles now. Job
Yes.
roles, the ecosystem. You mentioned the data scientists, data engineers, and the analysts, the data analysts. Okay, so I like the way you drew the scope. I said data scientists are for research. Earlier, you mentioned data engineering is for the way you move the data around. So maybe you can just expatiate little on that, show the difference between that and the analyst, because I feel in a way there's a convergence somewhere where they all have to work together to make the best use of the data that we have. Still have more questions, but let's just keep this for now. Yes. Thank you.
Okay, yes. A lot of the time, people like to think that there's a convergence, right? But one of the good things about the fields that we're in is that the names are very descriptive, right? So case in point is over here, we're very conversant with chemical engineers. And when you hear that someone is a chemical engineer, you have an idea of what sort of function the person will be carrying out, right? But if you heard that someone was a chemical scientist, you might have to stop and think and say to yourself, well, what's the difference between chemical engineering and chemical science, right? Or if you heard that someone was a mechanical engineer, you might have an idea of what you think that the person will be doing. But then if you heard that the person was a physicist, for example, you might then stop to ask yourself, okay, what exactly do you do? I know that over here, a lot of the time, you would probably find the physicists in the field of education, but in other places, you would, find them doing stuff, doing research, working in some laboratory, right? Not actually building engines of any sort. So it's the same thing with the analysts and the scientist, right? In analysis, interestingly, we have both data analysts and business analysts. And nobody ever confuses a business analyst with a business scientist. So the role of the analyst is to answer business questions. The role of the scientist isn't to answer business questions. And I put some things here. So if you look here, I said, what sort of gradient does this data exhibit, right? So you start with what is the gradient, how many minima and maxima. So again, when you're dealing with data, remember what I said, right? When we're doing the line of best fit, you could have had a linear equation back in secondary school. You could have had a quadratic equation, right? And when you have a quadratic equation, you have one point of inflection, right? You either have a minima or a maximum, but you have one point where the gradient is 0. And then if you have like a cubic equation, you have 2 points where the gradient is 0, where the gradient changes from one direction to the other. Because it's a cubic equation, there's going to be, you're going to have 3 gradients in that equation. Now, when you as an analyst, you are not going to management to talk about minima and maxima and loss functions, right? You're going to management to say, oh, looking at our production, we can see that this is what demand looks like. And so we're leaving money on the table if we don't have enough production at this time of the year, right? And then we're using up too much inventory this time of the year because we have very little demand. And so if we adopted something like just-in-time manufacturing, we would be able to predict exactly how much raw material we should order. So we are not stockpiling stuff. We don't have an unnecessary warehouse. We are not stockpiling things for 3 weeks that we don't need. Of course, again, the analyst needs to know what your supply chain looks like, right? So that's your data analysis and your business analysis. But when you come to data science, what you're saying is when we use these sorts of images where we're trying to tell what is in an image, whether there are weapons in an image, we see that if we use images of this size, it takes really long to train a model, and the model is not the best, even though the images are of a much higher resolution. However, we see that if we use square images of this resolution and we eliminate all the colors and we make them grayscale, it's much faster to train the model, and then the model is more accurate. Now, again, we see that if we use X approach to convert the images from this format to this format, this is what happens. As a result, if you, in fact, they might even come up and say, hey, we found a new loss function. If you use this loss function, you'll get better accuracy from your models for detecting X. Now, it turns out that a model that detects one thing is not necessarily the best at detecting another thing. Okay? So your model that is good at detecting weapons in images might not be the best kind of model to use in a self-driving car to detect things like potholes or even lane dividers. Was that helpful?
Yes, very well, sir. Very well, sir. So as you go on, you get the clarity.
Okay. Thank you very much. All right. So let's talk about the cloud. And the way to think about the cloud is it is simply another man's computer. So when you think about it that way, all of the abstract nature of the cloud tends to just fall away. So what is the cloud, and why do we use it? So you think of the cloud as something that lets you rent the kind of computer that you need when you need it. Now, when you need it is kind of subjective, because sometimes you need it and it's not available because other people have rented it. Because the cloud tends to have capacity. But basically, what we're saying is, let's go back to our training of ML models, but that's not the only application for cloud, right? Every other thing that you need a computer for, that is a server, hosting websites, storing videos, all of those things, you need servers for them. So you have two options. You can go out and purchase your server. You can go to, wherever your computer market is. You can go online, go to Dell website, go to HP website. You can spec out a server and wait for it to get delivered and run your workload on it. On the other hand, you can say, hey, I need to test this thing out immediately, and I need to rent a server that lets me test it out. To make matters worse, I only need this thing for an hour. So whose computer am I going to go and rent for an hour to test this thing out and then return it? And so that's where the cloud comes in handy, because the cloud lets you set up what you need as quickly as possible. Usually within minutes, you have your server up and you use it and you pay for what you use. Now, how you're charged for what you use is subjective. So you might be charged for a certain amount when the server is on. You might be charged a certain amount when it's turned off. You have ingress and egress fees. So ingress is, what's coming in, data coming in. Egress is data going out. But when you spec out, you have a few things that you're able to control. So the first one is what we'll call compute, which is what does your workload. So you think of compute like your CPUs, your GPUs, and any other processing unit. That's your compute. And then there's your storage, which is where does your data reside. And then there's networking and security. These four classes will, give you a high-level view of what the cloud is. There are other classifications. There are other services within cloud platforms that let you do things. So you have like operations, management, observability. There are other things. So this is not an exclusive list, but this is just a high-level look at what the cloud is. So let me go back and talk some more. So when you talk about compute, we're talking about what does your work. A lot of cloud providers will let you choose what sort of CPU you use, and not just the sort. So it's not like, do you want Intel or do you want AMD or do you want an ARM-based processor? No, it goes down to the nitty-gritty of saying, what type of processor do you want? How many cores do you want? So nowadays we talk about cores, we don't talk about physical processors. Of course, physical processors are still there somewhere, but physical processors, when you go and look at the spec, every processor has a core count and a thread count. So when you pick up the physical processors, you're able to allocate them, where you're able to say, oh, this processor has 32 CPU cores and 64 threads. Now I can allocate one CPU core for this task because it's small, or in fact, I can share the core depending on the overlay that you have. I can share the core because I know that there are two threads, so I can allocate one thread to this task and a second thread to this task. So your compute is where you choose. When you set up a cloud infrastructure, you can choose how many CPU cores you want to have. You can choose whether you want GPUs and how many of them. Your storage is what holds your data. So you think about it from the perspective of, if you're going out to buy a laptop, your laptop has a hard drive. What's the capacity of the hard drive? Is it 256? Is it 512? Is it 1 terabyte? Same thing with storage. But here, there are different types. So it's not just your hard drive. When you set up, if you're setting up like a virtual machine, and the virtual machine is not the only thing you can set up, but it's the basis for a lot of things. When you set that up, you can set the particular hard drive or SSD that you configure. But you also have access to other types of volumes. So we'll just call them volumes, or like buckets that you can think about. So for example, you might be used to hearing about S3 buckets, Amazon S3. S3 is simple storage service. So that you can request. It's not attached to the computer, but you have access to it where you can drop things. And so things will be things like image files or videos or other things that you can store for processing. So you can set up your data lake from your storage, even without the compute. The compute can, of course, access your storage. And then you have networking and security. They tend to be intertwined. It's kind of difficult nowadays to do networking without a bit of security, and to do security without a bit of networking. In the olden days, you would think about networking from, oh, does this computer have a network interface, right? A Cat5 or Cat6 port. I need a cable that will connect to the server and then connect to a switch or a router or whatever. Nowadays, what we have is software-defined networking on the cloud. And so you can choose your interfaces and choose what they connect to. Choosing your networking is part of security because you define virtual networks, virtual interfaces, and then you choose what can talk to what. Does it have a public interface? Is it a private interface? If it's a private interface, it means that only the things within that network can communicate. So kind of like it doesn't have a router. It's just a switch. That's how you think about it. On the security side, you have things like inbound and outbound configurations that you do. This is separate from, like the Cisco type of security that you do. You would have firewalls, you'd have firewall rules, but they're pretty kind of straightforward to configure, like what port am I opening or closing? What IP addresses am I allowing to access this? So you could have a port, but if you open only one IP address, that, then requests only coming from that IP address. What do I allow to go out? Threat detection. So cloud service providers have things where they look at traffic patterns and they can decide on what they think is fine or what they think is unusual based on those patterns. So, over the years, we've had these things called distributed denial of service attacks. Cloud service providers are able to detect those and shut them down. They can detect attacks targeted at different ports or just vulnerabilities that you've exposed. So for example, once there are things that are port scanners on the internet. Hackers use them a lot. They just try to scan every IP address and try to scan every port to see if you've suddenly set up a machine that is accessible from the internet, right? So networking and security keep you safe because they ensure that you don't just open that port. If you open that port, in a lot of places, you get a notice that tells you, hey, you just opened up this port and this is likely to happen. And these are various ways of mitigating some of those threats. So basically, talking about the cloud, what we're saying is, I need a server or I need infrastructure. I could go to Dell and HP and purchase that and wait a few weeks for it to arrive, and then I do what I need to do. It's fine. But what happens when I no longer need the server? And that's where the cloud comes in, right? So if you think about cloud service providers, these are companies that started out with some major infrastructure, investments in infrastructure. And then after a while, they didn't need that infrastructure. Now, there are various reasons why you don't need infrastructure. Sometimes you just upgrade, right? So, one man's very slow computer is another man's space rocket, okay? So one man's space rocket, very slow computer is another man's space rocket. And you think about it from the perspective of, if you think of Google, for example, they started out in the search business. And in order for them to run search, they needed, powerful computers. Now, they will depreciate their servers over time. And so they will replace them. So they might say, hey, we're going to replace our servers every 2 years or every 4 years. Now, if you gave me a server that was 2 years old, that's a 2022 server. I'll do wonders with that 2022 server, but it's too slow for Google. And so that's where the cloud comes in. So they are fine buying servers because there are people who need their slow servers in quote, right? But if I went out and I bought a server in 2022, I would have a new server, but then if I have more demand, then I need to go out and buy more servers if I'm not using the cloud. Now, the problem with that is, remember our analytics where we said, where do we have high demand and low demand? And that's because in most businesses, there's a period of high demand and a period of low demand, right? High capacity and low capacity. Think about it in any industry, even in power, right? In the power industry, there are times when the demand goes up. You have peak period and off-peak period, right? There are times when factories are running, there are times when factories aren't running, and so you just have excess power that you need to channel to people's houses. In people's houses, there are periods where it's extremely hot and they need to run air conditioning. There are periods where it's cold and they're not running air conditioning, but they might need to run water heaters. But is the power requirement the same? So in a lot of places, if you buy a physical computer, you don't necessarily use it maximally. You're not using 75% of the capacity every single day of the year. So that's where cloud providers come in. Now, of course, you can have your own private cloud within an organization. And the reason why you would have that is you want to go out and buy your physical servers, but that's because you have what we'll call customers within the organization. So there are people who require certain things, but they don't need them all the time, right? So some people need server capacity, and then when they're done, they want to shut down that server capacity. You don't want to go out and buy a physical server. You want to have, some beefy servers, and then you can allocate resources. And when they're done, they shut down, and then you can allocate to someone else. Now, if you have your own private cloud and someone needs resources and they're not available immediately, you'll then have to tell them, hey, you just need to wait a few days. These guys will be done with what they're working on, and then we'll have capacity to allocate to you. Okay, so that's the cloud. And the final thing is operations. So you might hear operations being referred to as DevOps. That's just developer operations. You might hear it referred to as DevSecOps. That's developer and security operations. You might hear it referred to as AI Ops. That's usually where the company is focused on artificial intelligence. Yeah, ML Ops. Yeah, ML Ops, AI Ops. And so operations is really just keeping things running. And why do we need operations? It's interesting, but it's because, when you talk to engineers, and I'm not talking about engineers outside of the computing space, I'm talking about engineers within the computing space, usually people who build software, they only know about building software. And I've been there, right? I've built software, and I built software that ran on mainframes, but I didn't know anything about setting up mainframes. And I didn't know anything about mainframe security, So engineers know only one thing. They know the solution that they're building. But if you ask them how it gets operationalized, how it gets productionized, how it's utilized, they don't know. Even, ML engineers and stuff like that, they'll tell you, here's the model. I'm done with the model. Okay, how do we put it into production? I don't know, or they might even try and say, hey, here's the model, and I've written some API endpoints. The interesting thing is, if you've come from an engineering background, you know that it's easy to write something that works very well when 10 people are using it, and then it just stops working when 1,000 people are using it. And as an engineer, all you know is, look, I don't know, this thing worked, right? This thing works. It works on my laptop, it works on my LAN. 9 of my friends are able to access it. I don't know why this thing isn't working when 1,000 people are trying to access it. And that's where operations comes in. So operations is responsible for scaling up resources, scaling down resources, just making sure things work, right? So they're responsible for productionization. Now, they also exist because one size doesn't fit all. So, how the kind of resources that Bank A needs to service its customers is not the kind of resources that Bank B needs to service its customers. A very simple example is, and I don't know if this has stopped happening, but there was a time in Nigeria where from the last week of the month to the first week of the next month, you are likely to get issuer or switch inoperative, right? The rest of the time, things work. When you try to make a payment, it just works. But there are certain times, once it's salary period, everything just starts to fall apart. And these things don't happen in other countries. You travel to other countries, you never try to make a payment and you get issuer or switch inoperative. You make an online payment. There's no time you try to make a payment on Amazon and you see issuer or switch inoperative, right? Even when they're doing Black Friday, they're doing whatever. Same thing with AliExpress. All of those guys, they're able to productionize. They're able to scale, right? Their DevOps is on point. But when you come here, and sometimes it's just the fact that someone knows that you need additional capacity, but the person says, you know what, since you don't need it permanently, let them just keep managing. We will manage, we will deal with the, sorry, your card didn't work. Okay, try this other card. Maybe this other bank will work, or wait 15 minutes and try again. So we do all those things. And that's where operations comes in. Operations is there to scale up and scale down services. It's there to make sure when the capacity isn't needed, we're not wasting resources. We're not just burning through stuff. When the capacity is needed, then we make it available so that we don't frustrate our customers. And then, of course, there's general maintenance. Things break. Things work and then they stop working. Servers work and they stop working. All sorts of things happen, right? Sometimes you need to change configurations. Sometimes you need to do stuff. Again, stuff that, engineers will tell you, this thing should just work, but you just need to figure out how to make it work. So that's the cloud and that's DevOps. They go hand in hand. And again, you need the cloud when you talk about the massive amounts of data and when you talk about your ML training and things like that. And I think that I have come to the end. Yeah, how did I get back here? Okay, yeah, so I've come to the end. Thank you. And let's take questions.
Wow, that was wonderful, sir. I think you deserve a detailed applause. Please let's give our presenter a detailed applause. Thank you so much, sir. That was wonderful. Yeah. So not to waste our time, I think we should go to the questions. I have a few questions too and comments. So please, do we have anyone on the call who has a question? Please just signify by raising your detailed hand and you'll be called, to ask your question or make comment. Okay, Toyib, Olalekan. Sorry, please permit me if I'm not using the right prefix or suffix. So please go ahead. Engineer Mr. Toyib Olalekan. Please go ahead, sir. Please, I don't know, is he audible? I can't hear him.
He says he can't unmute himself. Are you able to unmute him?
Yeah, he's no, you're muted, please. Go ahead. Okay, let me do it here again and unmute you again. Please go ahead and try. Oh. Okay, as an account, okay, he said it's okay. Before we go back to Mr. Lal. Yeah, so
okay.
we have someone on the call saying, my question as an accountant is on the analysis of financial statements. All right, sir.
Yes. Okay, so what's the specific question on the analysis of financial statements?
Engineer Mohammed or Mr. Mohammed, please go ahead, sir.
I am an accountant, and the question is how to use this data analysis for that purpose.
Okay. So the answer would be it depends. So a financial statement is usually a prepared statement. It's not the raw data. Okay. So there are two things. On the one hand is analyzing the raw data, not the financial statement, because it's the statement, depending on what you're looking at, it's either a personal financial statement or a corporate financial statement, right? But that is at the very tail end. Now, if what you're asking is whether you can prepare financial statements using some of the things that we've talked about, yeah, definitely. You can take your raw data and you can make use of maybe like a large language model and tell it how to arrive at a financial statement. So nowadays, there's so much progression, it's shocking, but you can either find a large language model that can take your raw data and give you financial statements, probably with a little bit of fine tuning, or you can give it a context. So a context might be something like giving it even like an accounting textbook, but that could have just way too many pages. But you can give it an accounting book that walks through the steps of creating a financial statement. I will give you that, right? If what you want to do is analyze the financial statement, again, you can start with a model, give it the financial statement, and look at the analysis that it gives to you. You can probably start with something like just ChatGPT. Now, there are again, some of the things we didn't talk about, security and privacy considerations when it comes to using AI. So you can put anything into ChatGPT. I've not tried DeepSeek, but there's DeepSeek, there's Gemini. You can put things into them, but if what you're working with isn't in the public domain, you might need to work with someone to set up a model for you and probably customize it, but a model that isn't going to send data back to wherever the model is coming from, that will carry out the analysis while still keeping things private, because privacy is a very important consideration. So yeah, I'll stop here and let me know if I haven't answered the question completely so I can say some more.
Mr. Mohammed?
Yes,
Okay.
we are okay with that. Thank you, sir.
Okay.
Okay. I think one point you made is to be careful of what we put in the public domain, especially ChatGPT. I think this is a wake-up call. Some of us just put everything. I think I'm also wrong in that aspect. And I think I should take note of that. Some very important, sensitive information, know how to go about it, not just train it all out in the name of trying to get AI to generate some information. All right, thank you for that, sir. So we have our very able National Financial Secretary. He's also an expert on the field, Engineer Chinwe. Please, Vivian, you have the floor, ma. Please ask your question.
Okay, thank you. Can you hear me?
Yes,
we can hear you. Good evening.
Yeah, good evening. Yes, facilitator. Thank you for that brilliant presentation. You literally covered most of the introductory aspects of this. Like I said, I think during the last masterclass, I'm actually an ML engineer, and I wanted to give 2 points. The first is to the question from the accountant. What you asked is a very interesting question, because I actually work kind of in the finance sector. I work in FIRS as an ML engineer, and what you're asking is basically some of the things that we do over there. So just to give you a little bit of insight on what you can start thinking of you can do with maybe machine learning is, if I'm sure you're familiar with financial ratios, with financial statements. You can use clustering algorithms to try and group different companies or group different financial ratios together to find out, to get some insights. You can use financial ratios of a company and even run some kind of predictive analytics on it to kind of predict where the country will be heading in terms of any of those financial ratios, liquidity ratios and all that. So there's a lot you can do if you can just try and do a little research on what I can do with ML and financial ratios. That's just like a pointer for you. Then back to the topic at hand. Like I said, Mr. Facilitator, well done. I just wanted to ask one question. When you were breaking down the different aspects of, different data roles, data engineering, visualization, like in my organization, we have a full-blown data department, and we have visualization units, we have engineering, but in reality, I sort of see that when you are working in the practical world, you now sort of have to, like, I'm just good at building algorithms, ML models, but I see that you now have to learn a bit of all of this. You have to learn a bit of data engineering, you have to learn a bit of visualization, and all that. Now, this DevOps you're talking about, because like you correctly said, when it comes to deployment of models, that's one of the things I'm trying to get my hands on, because there are software engineers that handle that. All I do is just, when I train my model, test it, I give it to them, they deploy. Mm-hmm. So what you're saying now, to what extent does someone have to start learning all these different parts? Do you think as an ML engineer, someone should also really hone on to deployment of models to the full technical aspect of deployment?
All right, that's a good question. And the answer is it depends, right? So, just to give you an analogy, and that's because I like analogies. Depending on your geography, you have to worry about different types of problems. As a Nigerian, everybody is basically a local government, right? You generate your power, you generate your water, you generate your security, which doesn't happen in the developed world. In the same vein, if you work in a large organization in the developed world, you're not expected to do multiple things. You're expected to do one thing. So basically, you're expected to just dig deep into your vertical and get really good at it, right? And so one would beg the question, so why have I done so many different things over the years? For one, it's interest. For the other, it's time. It's easy to learn something new every few years if you feel that you've mastered what you're doing. So what I'm saying is there are places where you don't even build, let's say you're an Android engineer, for instance. There are places where you don't build an entire application. You just build components. Like in Microsoft, nobody writes Windows, right? You write different components, you have a very large repository, things are brought together, and then you end up with the finished goods. So there are places where, as an Android engineer, you'll never write an entire application. You'll just write modules, you'll write subcomponents. And then, other people are responsible for bringing those things together and shipping them. But even shipping, is somebody else that does it. However, if you're interested in, knowing how to ship, it's perfectly fine to learn how to ship. Whether or not you'll be able to ship within the organization is another question, right? So case in point is there are places where DevOps is separate from engineering, and then there are places where DevOps is tightly intertwined with engineering such that you have to do your DevOps yourself. So there are other people who will look to ensure that you're applying the best practices for DevOps, but you won't just write software and maybe just do like a Git push and forget about it. But you have to ensure that your Docker files are right. You have to ensure that, whatever components you're using in the cloud are set up properly. So I don't know if I've answered you, but the answer is it's perfectly fine to learn. There's nothing that stops you. It's a function of interest.
That's fine. Thank you very much.
Thank you, sir. So engineer Toyib Lalekwan posted this question at the chat area. He said, kindly talk about the differences between DevOps, AI Ops, and the third one, I think the DevSecOps. Okay. Yeah. And mentioned during the presentation, which one would you recommend for an electrical engineer?
All right. Which one would I recommend for an electrical engineer? I think that's the difficult question. It depends on what the electrical engineer is trying to do. So remember, this is working on cloud infrastructure. So basically, the question would be, can a cloud engineer become, sorry, can a electrical engineer become a cloud engineer? That would be the appropriate question. And the answer is yes, right? Anybody can learn anything. The most important thing when we talk about anything, any sort of technology, is for you to know that as long as there's someone doing that job, you can do the job. Now, when people ask me for recommendations, I say it depends on what you're interested in, right? If you pick up anything that you're not interested in, and let me take a step back, there's money in everything, right? If you're a very good chef, you're going to make money. If you're a very good driver, you're going to make money, right? The fact that you can drive a car from Lagos to Abuja doesn't mean you can get into Formula One or MotoGP or any other thing. But if you're good enough to get there, you'll make money. So in the same vein, it's not, the recommendation is not based on where can I make money. The recommendation is based on, I feel that I'm interested in this. Now, if you don't know what you're interested in, then the best thing, and I do stand to be corrected in terms of careers, but I think the best thing is to just try and get an internship in something to find out how exactly it works, right? You could spend time actually going to take a course, but you don't want to take a 6 or 9 month course in DevOps and then take another one in AI Ops, just to figure out which one is right for you. Because again, the course doesn't really tell you what you'll be working in. In fact, you're better off just going on YouTube and finding, what does a DevOps engineer do? What does an AI Ops engineer do, or an ML Ops engineer, or a DevSecOps engineer? And then try to figure out whether that resonates with you. Now, in terms of differences, the difference is in what exactly people are dealing with. DevOps, you'll be dealing with the stuff that productionizes what software engineers are working on. So typically, those will be repositories and then maybe test suites, because you need to test code before you push into production. And then maybe containerization and then deployment. So deployment to what? Rarely VMs, but potentially VMs, sometimes to Kubernetes clusters, sometimes to some other fully managed cluster type resources. That's DevOps. So you're dealing with developers. AI Ops, on the other hand, you're dealing with machine learning and AI type models that need to be put into production. Is that different from what software engineers are building? Yeah, sometimes, because again, you have libraries that you need to worry about that software engineers never touch. So things like TensorFlow, TensorFlow Extended, TensorFlow pipelines, things like that you need to productionize. There are overlaps, so you need to know, things like Docker engine and stuff like that. DevSecOps, on the other hand, has security incorporated into it. So cloud environments, again, they're like a sitting duck. They're out there. They're very large targets. Some people's full-time job is hacking into things, locking them up, asking for, ransom and things like that. So there are people whose full-time job is security. For example, if you use a mobile banking application, is it possible for someone to figure out how to steal credentials from that? Is it possible for someone to look at logs in that? Is there some sort of porosity between the application and your API server on the cloud? Those are all DevSecOps, should I call it a role, or the scope of what someone in DevSecOps will be doing. So again, I don't know if I've properly touched on it, but please give me feedback.
Okay, thank you so much, sir. Time is fast spent, but I'd just like to talk about a few things quickly. I just had to, we've been talking about getting skills, learning extra skills and all that. And my own take, I mentioned convergence. My own take is there's a place for specialization and there's a place for convergence. You mentioned something about in a company where you learn how to manufacture the product, then you can learn how to do the shipping and all that. I always use this analogy of a movie. You know, the movie comes out well when everybody's specialized, good at what they do. The person taking care of the lighting, the producer, the audio person, the person editing, and all that. They have to be very good in what they do, you know, to be able to get the best out of the movie. But at the end of the day, they work together, you know, to produce that particular movie, you know, and that's so I believe in specialization first, be good at what you do, then converge with others. And while you're converging with others, I think you can learn one or two things and you can share ideas, you know, co-creation and all that. So that's for that. And looking at your presentation now into different areas, look at education. I'm so glad there's a, you know, for me, I don't really like maths in quotes. Why? Because it's very abstract, very abstract. But there's something you mentioned today. You said you mentioned about is it AI or something being the GPUs, you know, being good for linear algebra. You know, you mentioned something like that. So if I know that it can be applied in that area, I think I'll be more interested. And I think we should use this approach to teach, you know, people who want to learn, even the younger ones, even the ones that are the professionals already, that, you know, to get them interested in these thing areas or fields. So I'm just saying that because I like the way you presented it. It makes me now interested. Okay, let me go and look at that linear algebra again. How does it apply? But before, I didn't want to talk about it. I don't want to look at it, you know. I just want to do my thing. So I think that's a good one, sir. Then for the practice, yes, you mentioned the DevOps. And I think there are different, I just want you to expatiate more on that. There are different platforms for the DevOps because you said something about the DevOps is you can have different, you know, platforms. I know AWS has their own, Microsoft has their own, Google has their own. Is there a point where, you know, you can have some basic skills that you can, as an entry point into the DevOps, you know, ecosystem, then you can now specialize in any one of the products. Is there that kind of, that's that question for that. Then for data management, you know, you said data is the new oil, right? And if we say Nigeria, I think we should have one of the largest amount of data in the world. Nigeria, even if majority, if people want to say that, the majority is about problems and all that, I think it's still good for us because is it Isaac Newton that created or who created the electric bulb? I did it 1,000 times, and they said you failed 999 times, and I said no, I only found out 999 times of doing something better. So I think that can help us grow. So my question, sir, is as professionals, you know, we have accountants here. I'm so happy. We have scientists here who have joined us. How do we ensure that we have more structured data in all we do? You mentioned different ways of storing data, you know, and you know, to me now, I'm feeling. I think they're all on different levels. But I think one that, as professionals, building it for our industries, different industries, should be data lakes. Data lakes where you have everything aggregated. So what's our approach as, you know, you should have that conscious mindset of ensuring that the data we churn out there, is useful in some way. So please, sir, if you can just give us some tips on how we should be responsible as professionals with our data, the data we churn out there, and probably the ones we see, how to ensure that, you know, they are useful to our communities, you know, for our communities more informed. So I'll leave it at that, sir. So I don't take
Okay.
more time.
All right, that's fine. So yeah, thanks for all the feedback. There was a bunch of feedback, and then I think there were two specific questions. The first one, so if I forget the second one, which is the very last one that you asked, please remind me. The first one is on DevOps and getting started. So you would think of DevOps kind of from the perspective of like flying a plane, right? So there's the general theory of flying a plane, which is if you're a pilot, you're a pilot. And then there's the practical aspect of flying a plane, which is the fact that you can fly a, let's say, Boeing 747 doesn't mean you can fly a Dreamliner, right? So you have to go and learn how to fly a Dreamliner. But there are skills that are transferable, and that's the beauty of like anything you do. In a lot of fields, skills are transferable. Right. So when you look at something like developer operations, the question is, how do I get something to the point where people can use it? And again, the answer is always it depends on what you're doing. A. B, it depends on the advances in technology. So there was a time when making sure that people could use something was a function of something called either horizontal scaling or vertical scaling, but it was on the bare metal. What that means is you would start out with one server, and then you would observe your traffic. So you'd start out with an oversized server, and you would observe your traffic continuously. And then you would have a cutoff point where you'd say, if this thing gets to this point, I will either A, replace this server with a larger one, which is vertical scaling, or B, add a second server that is more or less the same size, but that doubles my capacity. Nowadays, we don't do that very often. We don't do it on bare metal, right? Virtual machine clustering. But there was a time when we did that. It still has its benefits. So if you're doing something like high performance computing, or where you're setting up, specific types of clusters like GPU clustering and stuff, you would do that. Or even just, setting up a cluster that would let you virtualize other things. But what you then have now is you have something like containerization. And containerization has its benefits in the sense that if this thing works within the container, it will work anywhere. So if you deploy it on an Intel machine, if you deploy it on an AMD machine, it will work. And so containerization is kind of like a baseline starting point. If you can containerize applications, then you're one step closer to deployment. So you can containerize and you can deploy, then you can worry about scale. And then you have to worry about scale, but the environment in which you deploy and you scale can be different. So for example, we have what's called Docker containers, and then if you want to deploy, you can deploy to Docker Swarm, or you can deploy to Kubernetes. But if you're on different cloud environments, how you set up your Kubernetes cluster is different. You can even set up your own local, test bed as a way of getting started, right? So I'm answering the DevOps part of things, where there is a baseline that you can learn that gets you out the door. And then when you get on a particular cloud, you learn, or you find out how exactly to productionize on that particular cloud, which will be slightly different. So setting up a Kubernetes cluster on AWS will be different from setting one up on Azure. But once you have the cluster up, deploying into the cluster is the same. But again, managing the cluster, scaling up and scaling down on those different clouds could be slightly different. Case in point, the commands, the entry commands would be different, but the output, because what you're doing is you're defining a desired state, the output, the end result will always be the same. Okay, so that's that. The second one, talking about the data, and Ibrahim, I'll come back to your question. So we haven't, circumstances haven't overtaken your question. Second one, talking about data. So I think the starting point might be for us to look at how others are collecting and storing data. So recall there's a lot of data in the public domain, right? So if you think about an industry and you put in that industry name, so don't necessarily put in like a company name, but put in an industry name and then, put in data, and you will see how maybe different actors in that industry around the world are making public data available. That then gives you a sense of, oh, we could do this, right? So one example, for example, is you've got police crimes database in the UK and in the US, right? What that does is it tells you, hey, if we wanted to make crime data available here, this is the kind of data that we would make available. And why is that useful? It's useful because it helps you with planning your movement, right? It's useful with helping with predictions. So for example, there is there's a New York taxi cab data set that it's probably running for like 20 years or something like that. And that helps you with building stuff like Google Maps or Uber, because it helps you learn how to predict traffic patterns and routing and those sorts of things. So if we want to start out with collecting and storing data, we can look at examples of what people have done, right? And then we can start. The problem is starting. So we have a cold start problem. But once we've started, then we can expand the scope of what we do. We can decide based on our own context to store additional data or different types of data. So I hope that was helpful.
Yes, sir. Yes, sir. So we just have to start, a cold start. Yes. And we need people like you
Thanks.
for more of the advocacy, since you know what should be expected of the input and the output. So thank you so much for that. So one more question before we close up. So you sir just posted one. How does
Yes.
one go about starting up as a civil engineer to get into the field of data? And what is the role of community in learning about AI? How does one go about getting a firm foundation in the field? I know you've answered that, but maybe just to...
Yeah, not necessarily. So there are courses. One of the things I didn't say is that there are courses. These big companies, they always have courses. IBM has courses out there for all sorts of things. If you even check YouTube, IBM, so just search for IBM on YouTube and put in what you want to learn, and you will most likely find something. IBM used to have, I think it was called Big Data University. I can't remember what it's called now, but IBM has always been huge on learning. Google is huge on learning. They have some courses on Coursera. Yeah, Microsoft also has courses. So all of these big cloud providers, they have courses. On data, again, I think Coursera is a good starting point. Udacity is another good starting point. It's just that Coursera is relatively cheaper than Udacity, but I like Udacity's education format. You have a final project and other things. So whatever it is you want to learn in terms of just getting started, search for a course, but take a course that has quizzes and, if possible, mentors and project work, right? So it doesn't have to be real time, but it should have these characteristics. Unless you are really advanced, avoid anything that just requires watching, because you can fall asleep while you're watching. So I've never been a fan of what's this other one? So there's one of these learning platforms where you just go and watch videos from beginning to end. I've not been a fan of that. If you want to just watch a video, go on YouTube and watch a 30-minute video, 60-minute video. Data, these guys, Tableau are very good. Tableau education is very good when it comes to teaching about data. AI, Udacity is very good. In terms of learning communities, I mean, why did we all go to university? It wasn't really about the learning, it was about the community, right? If you went to a university and you were the only person in your department and you didn't make any friends, I don't know how you'd turn out. So again, you can't really learn anything in isolation because there's just so much coming out nowadays. So you need to be in a place where people are talking about what's new or what you're struggling with and where they can give you a different perspective. So community is really important. And firm foundation, really, it's just experience, it's time, right? So if you want to get a firm foundation at anything, it's just constant repetition. You have to just keep doing it. We all know how we learned, various things, how to walk, how to ride a bicycle, and then academic work. You just have to keep doing it and doing it until you get it right. Okay. Oh yeah, cognitive class. Thank you, Engineer Chinwe. IBM is now cognitive class. Yeah, so you can look that up. They've got good material as well. Yeah, Free Code Camp is also. I think if you use Free Code Camp with the website or the portal, then you'll get something really good. Yeah. So thanks, Engineer Chinwe, for all the comments. Everyone, please just go read her comments. Right. So
Okay.
I think I've answered all the questions. Back to you, Mr. President.
All right. Thank you so much, sir, for that. Yeah, I just want to add something. I think Nigerian Institute of ICT Engineers also plays a good role in helping any engineer start up, in the AI, just like what we are doing now. I always say the best way to learn is to learn from the master in that craft. And we have the master here, and I'm sure, years of learning, you brought it to us in some minutes. And so that's a wonderful one. And I want to say that with the support from our organizing partner, we're going to make this more available. I'm hoping, sir, that we're going to have some training classes after this, to let give a platform for others to learn. And I think it's good to learn from YouTube videos. Some people are very good with self-learning. But I think one of the best ways to learn is to, you mentioned community, which we also offer. Yeah. You see, Engineer Chinwe already giving us some ideas. They're giving us some ideas. Before you know, the person grows. And so I think we also encourage our local platforms like ours. And so that's just my point on that. Thank you so much, sir. So again, I want to thank you, sir, Mr. Robert, for this time. Sincerely, I've seen a lot of the great work you're doing. Having you here, it's a great privilege, to be in our midst. We thank you especially today. And I want to thank everyone on the call. I can see a lot of our senior engineers, our guests, the executive members. I want to thank you all for this successful 7x7 masterclass series. So we ended well. I think this is one of the best classes we've had. So I want to thank everyone. I want to say there are two things that are left for us to do as the organizers, is to ensure that everyone gets certificate of participation. So just give us some time. We'll get that done. And for also our facilitator for certification of certificate of facilitation. So I appreciate you, and also to document this class. So thank you all. Please stay tuned for all classes. This is what we are all about as a professional body, to ensure that the right skills are put out there, and create a community to back that up. Thank you so much. Let's take our time. We're closing at exactly 7 o'clock. I wish us all the best and a wonderful holiday. Thank you again. And to our organizing partner for this happen, I want to thank you again, sir. God bless you. Have a wonderful evening. Good night, everyone. Thank you so much.